Hi guys, today I'm going to talk about the collapse of the second Narrows Bridge. One of the most fundamental jobs of an engineer is to compare loading conditions to strengths. If the loads exceed the strengths, you know you got a problem. Buildings and other structures face a huge variety of loads, including floods, snow, rain, ice, earthquakes, and crowds of people. One of the most interesting forces faced by civil structures is the wind. A bridge is a quintessential civil structure. Humanity's need to get from one place to another without getting wet is as old as history itself. And for so many years, there was one force with which the bridge engineers had to contend: gravity. The fundamental question of bridge design was this: how can we hold up the structure itself and all the people and vehicles that may cross against the force of gravity pulling them downward? And secondary to that, how can we do it economically with the least cost to the public, since most of the bridges are funded by the taxpayer? So, over time, bridge designs evolved with our understanding of structural engineering and ability to create better construction materials into lighter and more efficient shapes. One of those shapes being the suspension bridge, cantilever bridge. Today, we're going to talk about the Second Narrows Bridge. Second Narrows Bridge is officially called the Ironworkers Memorial. It spans over the Bernard Inlet in Vancouver, Canada. It's a cantilever type bridge and it spans over 1,292 meters. The center span of the bridge spans at 335 meters, which is the second longest cantilever in Canada, second to the Quebec City Bridge. The construction of the second Narrows Bridge started in the year of 1956 in the month of February. After many hardships, it has been completed on the 25th of August 1960. The bridge is part of the Trans Canada Highway, which connects Vancouver to Canada. This right here is the current image of the second Narrows Bridge. History of the first second Narrows Bridge. The first bridge across the second Narrows of Burrard Inlet was completed in 1925. It provided access for cars and trains, but its bascule, a pivoting section that is raised and lowered using counterweights to allow ships to pass, proved problematic. The bridge was hit numerous times by ships, by the freighter Ariana in 1927, by the Norwich City in 1928, and by the Losmar in 1930. In September of 1930, the Pacific Gatherer got wedged under the bridge and ripped away its center span. The bridge was sold to the provincial government in 1933, repaired and reopened in 1934, with the bascule replaced with a center lift span. Traffic interruptions were legendary on this bridge. In 1952, for example, some 28,000 boats passed under the bridge, requiring the lift to be raised over 5,000 times. A large lift bridge was built immediately to the east of the original bridge in 1968, and the old bridge was removed in 1970. Various options were considered to relieve the growing traffic problem, including a causeway, but the provincial government decided on a new bridge at the Second Narrows. It would be located just west of the old Second Narrows Bridge. The bridge was designed by Swan Wooster Engineering and Company and would be a deck-type cantilever with the roadway supported by steel. Keywood Raymond were contracted to build the piers and the Dominion Bridge Company to build the steel. The Dominion Bridge Company had built many of Vancouver's early landmarks, including the Hotel Vancouver, the Patullo Bridge, and the Lions Gate Bridge. The consulting engineer in charge of the bridge was Murray MacDonald. The sequence of events leading to the collapse were followed like this. On the 15th of May 1958, assembly of the steel span and temporary scaffold had been started. On 20th of May in the same year, the steel span hoisting was initiated and was completed on the 1st of June. On the 10th of June, there was a shift in weight distribution during maneuvering of the cranes, which were lifting heavy beams of metal, steel. On the 15th of June 1958, there was a failure of temporary work platform, also known as the scaffolding, and the collapse had occurred near quitting time on June 19th of 1958. At about 3:40 p.m., ironworkers toiling 40 meters above the inlet heard a horrific noise as span 5 began to crash into the inlet in a mass of tangled steel. The momentum dislocated the columns of Pier 14, causing Span 4 to lose its grip and tumble into the sea. 79 workers fell into the sea, among them 19 were dead, including 14 iron workers, 3 engineers, a painter, and a commercial diver who died few days later when he drowned trying to recover a body. 20 others were seriously injured. After the disaster, a royal commission determined that the reasons for failure were complex, involving a faulty engineering calculation on a temporary support or false work. The term false refers to the fact that the structure was removed once the span reached the next pair and becoming self support. The design of the span 5 false work was done by engineer John McKibben, who made several errors that were not caught by the engineer in charge, Murray McDonald. The historian of the bridge disaster, Eric Jameson, has noted, however, that McKibben's role in the collapse was only one factor. Other factors included questionable steel quality and lacks of engineering practices. McKibben was killed in the collapse of the Ironworkers Memorial Bridge. Bridge design overview. In the design, the engineers drafted a blueprint considering the geography, expected traffic load, environmental conditions, and the challenges posed by the waterway. Detailed calculations and simulations for the structural integrity were also taken under consideration. Before construction, a solid foundation was very crucial. Involved sinking support columns and or piers into the water or seabed. That provided a stable base for the bridge structure. Erection of the structure. Steel girders and sections assembled and were lifted into place using cranes for the process. This was a crucial phase as we were hoisting a substantial amount of steel span into the support structure, establishing the bridge's integrity during this phase. Collapse factors. Collapse occurred during this critical phase of erection. Temporary work platform called the scaffolding had failed, and the design inadequacy for weight and stresses during the steel span positioning. Sudden shift in the weight while distributing the span and maneuvering proved disastrous. The collapse resulted in a tragic loss of 19 lives. This triggered a substantial reassessment of the safety protocols and emphasized the critical need for stringent safety measures, highlighted the importance of robust design and comprehensive structural support during the complex construction phases. The factors leading to the collapse are as follows: structural weakness, which resulted from design errors in temporary work platform, also known as the scaffolding. Vital for providing a solid foundation for the 367-foot steel span, had critical design weaknesses. Lack of consideration for the enormous weight and forces during the crucial phase also affected in the weakness of the structure. Scaffold's role in supporting the steel span and distributing stresses efficiently was inadequately addressed in the design. The next factor leading to the collapse was the weight distribution. The scaffold depicted as an intricate network of steel beams and supports. Lack of appreciation of dynamic loads on the steel span's movement and adjustment led to the breakage of the steel in the scaffolding. Inefficient weight distribution leading to compromised integrity of the scaffold. Hoisting and maneuvering of steel members during the construction process revealed a sudden and unanticipated shift in weight. The scaffold was ill prepared to handle dynamic stresses during the critical positioning phase of the bridge. The stress analysis report had indicated an inadequacy in the scaffold design. Another factor leading to the collapse was the material quality. Material quality and strength was compromised, especially in the steel department. The steel which was brought in from England was not up to the mark, which led to the weakness in the structure. Insufficient steel reinforcement in areas of the scaffold were also observed. Material analysis raised concerns about the steel which was used in the construction. Lack of proper reinforcement contributed to the scaffold's inability to handle the steel span's weight. The construction process overview went somewhat like this. During the preparation process, the temporary scaffold was set up on the ground and it was assembled later to provide support for the steel span. Hoisting of the steel span into place was done by the use of cranes progressively. The scaffold's role was to support in distributing the weight of the steel span. Maneuvering and erection was the most critical phase of the whole project, as this is where the bridge had collapsed. This is where the bridge was being positioned, and the abrupt change in weight distribution during maneuvering resulted in significant strain on the scaffold, which led to the event of bridge collapse. A lot of human errors were observed in this project. Started with lack of adequate planning. Comprehensive planning and stress assessment was missing on the temporary scaffold. Insufficient consideration of stresses and dynamic stresses during the lifting and positioning of the steel span were also not taken into consideration. The safety measures on this project were very insufficient, and safety protocols during critical phase were potentially inadequate. Enforcement of safety measures might have been lacking, contributing to the collapse. Misinterpretation of weight distribution was the main cause of the collapse, as scaffolding was not designed well enough to handle the maneuvering and erection and hoisting of the steel span of the bridge into the place. Lack of accurate understanding of the stresses on the scaffold during the maneuvering was observed. Safety measures. During 1958, the safety measures and protocols were not as stringent as they are now. Basic protocols were followed, such as helmets and harness. The safety training was less extensive for workers, due to which they were not aware of how to proceed during such an event. And even the safety awareness was very limited, and safety culture was not deeply ingrained. This right here is a picture of how less they were secured during the project of the second Narrows Bridge. Even the inadequacy of stress analysis on the scaffold was considered a human error and a safety measure. Design flaws compromised the load bearing capacity. Dynamic loads were not at all taken into consideration. Human error and oversight played a significant role in the loss of life. Misinterpretations of weight distribution was the main cause, and absence of comprehensive safety culture. The ironworkers were working 40 meters above the inlet heard a horrific noise. Span 5 of the bridge had collapsed, followed by Span 4. Workers were carrying heavy tools, and no safety nets or ropes were available. Workers were dragged into the depths as they were attached to the steel beams. 18 of the 79 workers that fell were killed, including 49 workers, 3 engineers, and 1 painter. Later, the commercial driver, who went in for a rescue mission, which turned into a recovery mission, was also dead. 20 others were seriously injured, leading the total death toll to 19. This event of the Second Narrows Bridge has led to many changes in terms of safety, engineering, and material analysis. Before the collapse, the safety protocols are not as stringent as they are now. Rudimentary safety measures were taken, just focusing on personal protective equipment. After the collapse, there was emphasis on complete and comprehensive safety. Rigorous safety training for hazard awareness, emergency response, and proper use of equipment was been given to all the workers on the site. Improvements have also been observed in the structural and design department of engineering. Before the collapse, there were less structural analysis reports and not very stringent laws, and supervision was present on site, which contributed to design flaws, especially in the critical components such as scaffolding. After the collapse, we've seen a significant shift towards exhaustive structural analysis to prevent such tragedies. Engineers incorporated advanced simulation tools to anticipate and mitigate potential weakness. Softwares have also been developed, such as SolidWorks and 3ds Max and AutoCAD, which would predetermine the stresses and loads on a steel member, which would be very helpful in the future. Technological advancements and legislative changes have also been observed before and after the collapse. Before the collapse, limited safety technology and basic fall protection systems were used. Potentially less stringent legislation and construction safety was observed. But after the collapse, technological advancements in the safety equipment, including advanced fall protection systems and real time monitoring, were being observed in the construction field. Legislative changes with stricter regulations and mandatory adherence to safety standards was observed. Regular inspections, supervision, and severe consequences for non compliance was observed after the collapse to prevent such serious tragedies in the future. The Second Narrows Bridge collapse caused an international impact which led to global reassessment of construction practices and safety standards all over the world. It also led to educational initiatives which led to increased emphasis on education and training of safety and structural engineering. Integration of case studies on the Second Narrow Bridge was also included in academic programs. Continuous improvement of safety standards and stress analysis was also observed on sites. It was a reminder that safety is a dynamic discipline. Ongoing evolution of construction practices, safety regulations, and engineering standards to address emerging challenges and technologies. We can conclude that the disaster of the Second Narrows Bridge resulted from a combination of structural flaws, material deficiencies, and human errors. Inadequate design of the temporary work platform, the scaffolding, and insufficient material reinforcement and a lack of comprehensive safety protocols during construction played pivotal roles in the collapse of the Second Narrows Bridge. The Second Narrows Bridge collapse serves as a poignant reminder of the importance of prioritizing safety in construction and infrastructure development. This leaves an enduring legacy that shapes the industry and emphasizes the commitment to continuous improvement and innovation. It opened on August 25th of 1960 after many years of construction struggles. In 1994, the bridge was officially renamed the Ironworkers Memorial Second Narrows Crossing to honor all the workers, including the four others who had lost their lives during its construction. On June 17th of 2008, on the 50th anniversary of the collapse, the Ironworkers and WorkSafe BC partnered to honor the memory of the dead workers in a ceremony. There have been a number of tributes to the fallen workers, including a song composed by Stompton Tom Connors, "The Bridge Came Tumbling Down," Jimmy Dean's ballad "Steel Men," and Gray Geed's Book of Poetry. And I finally want to thank everyone for watching my presentation on the Second Narrows Bridge. Thank you.